So in our continuation of learning more about probability in Chapter 7, we've done some basic probability calculations, but now we're going to start getting a little bit more complicated with them. And as we get into more complex situations, we start looking at certain rules to make the process for us easier to know how to handle and to be able to calculate them accurately. So we're going to learn some rules of probability. But before we get into that, let's see if you can, figure out what goes on with this kind of circumstance. And basically, you don't get out of any course that deals with probability without dealing with a course that dealing with several questions that deal with you throwing a pair of dice. So, this example, a pair of dice is cast, and the number that appears uppermost on each die is observed. Most of you know how dice work. I'm sure. I mean, even if you don't like play in Vegas, I'm sure you play Monopoly or some other board game where dice was used. So I think you all know how dice works. Refer to this experiment and find the probability of each one of these events. So you're looking for the probability that the sum of the numbers is an even number, the sum of the numbers is either 7 or 11, and the probability that a pair of ones is thrown. So take a moment, think about how you would calculate these probabilities, and then we will go over it. All right. So, notice there's not a whole lot of like initial information. They're not telling us how many things out of a set we're taking or things like that. I mean, they're expecting to know something about dice, and we have two different die here, and each one, could range from 1 to 6, 1 dot to 6 dots. And you're also working under the premise that the what one die will land on is independent of what the other one will land on. It isn't like, if one rolls a 1 and the other one's going to not be able to roll a 1. There's no mechanism in there that makes that happen. So, you know, um, so one of the things that you have to kind of think about though is like, well, how many different outcomes are there? Because remember, that's one of the things we need to know for probability. And then you would need to figure out, well, how many different like outcomes gives me an even number when I do that? So you need to have some sort of idea or be able to define these sample spaces kind of accurately. So, you know, and we're eventually going to learn how to basically count, and figure out these things a little bit more easily. But for the time being, we can use this little table here. And as you can see, these are the results. If I like, the very first one in the upper left-hand corner, if I have a 1 and a 1, that gives me 2. And each one represents the total I get, and what you see in the row and column headings are basically the die that are involved. So I want to see, and if you look here, because these two dice are independent of each other, one does not affect the other. I can see that by the size of the blocks that basically there's 36 different outcomes here. Yeah, you might be saying, well, you have 5 being mentioned like 4 times, but there's different combinations of dice. And as I said, since one's independent of the other, it does matter to a certain degree if the first one's a 3 versus the second one being a 3. Because they could both be 3 at the same time. The first one could be 3 and the other one not be 3. So it is more of a permutation type scenario because it does, we're looking at this from a standpoint that it does matter to a certain extent. So the first one, the sum of the numbers is an even number. So I'm looking for any of the totals that are even. So what I see here is I have all of these represent the totals that are even. And I can see I have 18 of them when I count all the green spaces. So basically the probability of the sums of the numbers are even is going to be 18 over 36, or about 0.5. Seems to make sense because, on a die, half the numbers are, even. The other half are odd. I mean, so some people think that's different because you're combining two dice together, but it doesn't. I mean, it's just basically because if you combine two evens or two odds, you get an even. If you combine an odd and even, you get an odd. So I mean, each one of those can happen just as much as the other one. So for the second one, you're asked, okay, what's the probability the sum of the numbers is either a 7 or an 11? So again, I'm looking at these situations here and counting them. I have 8, and that's 8 out of 36. So the probability of me getting a 7 or an 11 when I total the die is 8 out of 36, which is 2/9, which is 0.2 repeating. You're going to see oftentimes when we deal with decimals, I mean, we try to write the decimal because it's easy to convert to percentages, because oftentimes when you're asked about probabilities, you say, well, what's the percentage? It's just an easy transition. However, in some cases, you might get some decimals that don't terminate. So either you need to make sure if you're running as a decimal that you're trying to be as exact as possible. So if it does have a repeating pattern, you state that. Now, if it does terminate, but because of the numbers involved, you don't see it on your calculator, sometimes it might be better to leave it as a fraction. So just to be even more accurate. So you'll see probabilities written out both as decimals and fractions. They're equal as far as giving values and accuracy goes, but in some cases a fraction could be more accurate and more exact than a decimal, especially if rounding's occurring. And of course, the last one's pretty easy. There's only one outcome that gives me a total of 2. And that's 1 out of 36, which is about 0.02 repeating sevens. So you're talking about roughly 2.8% of the time you're going to be rolling what they call snake eyes. So now let's get into some more rules here. There's properties of working with probability, so let's talk about a couple of them. The probability of any event is considered to be greater than or equal to 0. So I can't have negative probabilities. I can't have anything over 100% either. Because the probability of my entire sample space is 1. So any probabilities that I'm coming up with, once I've named all the potential outcomes, the probabilities for those outcomes, if they're totaled together, should be 1. Now, occasionally, if you're doing some rounding, it may be off by like a 0.0004 or something, 0.001 or something like that, something small. That's okay because it's just rounding. But you can't have your probabilities being under 1 as a total, because that usually means that you're probably missing a possible outcome and you need to figure out its probability. Or you can't have it be over 1, because we can't really have over 100% in this kind of context. We're not talking about growth or anything. We're talking about how many things out of all these possibilities can this happen. Well, the number of possibilities is the number of possibilities. That's it. You can't have more outcomes than possible outcomes. And the first thing they tell you here, if E and F are mutually exclusive, then the probability of E or F is just me adding those two probabilities together. So basically, if they're mutually exclusive events, and I'm looking for a probability of one or the other happening, I just have to add the two probabilities of the single events together. That's going to be different if they're not mutually exclusive, and you're going to see a formula we use there that looks very similar to something we used back in the previous chapter. So let's see if we can make use of this to some degree. So we have example 2 here. The following table gives us the number of people killed in rollover crashes of various types in vehicles in 2016. So there's your data. If a fatality due to a rollover crash in 2016 is picked at random, what is the probability that the victim was in A, a car, B, an SUV, or C, a pickup or an SUV? So take a moment, calculate these. You're going to be asked to round them to a certain decimal place. So, be careful with the rounding, and then we'll go over it. Okay, so when you're dealing with probabilities, I mean, you first have to make sure you have each outcome here. You're looking at these rollover crashes. They're all rollover crashes. And so you have the number of deaths in each type of vehicle. So what you want to do is first figure out what is your sample space. How many different individuals are in this? So there's 10,656 different rollover crashes in this study. So I need to know that because, I need to know how many different, your total space is, so I can come up with the probability. So if a fatality is picked at random, what's the probability it was by a car? Well, that would be 4,768 out of the 10,656, or 0.447 repeating. So if it's an SUV, well, that's just 2,448 over 10,656, or 0.2297 repeating. So the first two is, not part of the repeating pattern. A pickup or an SUV. Now, this is pretty straightforward because of the fact that, if someone was in a crash, they could not have been in a pickup and an SUV at the same time. They're talking about what they were riding as passengers. I guess if a really bad accident and you're not wearing your seatbelt, I guess you could be in one vehicle, go to the other. I don't never hear that happening. But, we were talking about what were they a passenger in? And we're talking about a rollover crash, so usually those type of crashes, you're not talking about a multiple vehicle accident, a lot of times either. So basically, for me to figure out this probability, all I really have to do for this is just look at those two numbers together, either add those together, take it out of 10,656, or I take the individual probabilities and then add them together. And when I get that, I get 0.4870495 repeating. I put more decimal places here, or indicated more decimal places than I had you do on the example, but, there we are. Let's look at the next example. In a survey conducted to see how long Americans keep their cars, 2,000 automobile owners are asked how long they plan to keep their present cars. The result of the survey follows. So you have X represents the number of years they plan on keeping their car, and the number of respondents who gave that as an answer. You're asked to find the probability distribution associated with these data, which, most of it is still there. Most of it's done. Then you're asked to find what's the probability that a random person from the study plans on keeping their car for less than 5 years, and what's the probability that a random person from the study is going to want to keep their car 3 or more years. So take a moment, think about this and what information you have in the table, and come up with the answers to these. Okay then, so as you can see here, we have these smaller subsets. Now when they say less than 5 years here, well, before I even get into that, I do want to figure out what the total number of respondents are. Make sure it is accurate. It did tell us 2,000, but I want to make sure it is 2,000. It's always good to double check that to be sure that there's no miscommunicated information here. Because I should definitely, if I'm looking at the data itself, I should use whatever I get out of the data. And this does say 2,000. If there was a discrepancy, I would go with what the data is listing, not with how it was summarized in the paragraph. But the first one I'm looking to see, what's the probability that the random person is going to be from a group where X is less than 5? Now, I have to look at this. I have one group here. Use my laser pointer. One group here that's less than 5, but these are all less than 5 as well. So it stands to reason that, I'm going to be looking at these groups together. And these groups, the way they're defined, I can't be in more than one group. It's one of these smaller groups. I could say less than 5 and make that a subgroup, but that's a subset. It's a grouping of 3 of these. So I'm just going to total the 60, the 440, and the 360, and I'm going to take that out of 2,000, and that gives me 0.43. So about 43% of the respondents say they plan on keeping their car less than 5 years. What's the probability for 3 or more years? Well, again, 3 or more. I do have this one here that shows X being more than or equal to 3. But all these other ones are also 3 or more years too. So any of these categories starting here moving down is going to be something I need to consider for this. And so I would add those together, divided by 2,000, and I would get 0.75. So about a 75% chance that a random person is going to be keeping their car 3 or more years. Now there's a more specific addition rule. We learned before if they are mutually exclusive, then we would just say the probability of E plus the probability of F is what the probability of E or F is. If they're not mutually exclusive, much like we did for like counts in the previous chapter, if I'm looking for like the number of elements in E or F, I would usually take the number that's in E plus the number that's in F, and I would subtract away the number that are in both. Same thing here for probabilities. I'm going to do the probability of E plus the probability of F minus the probability that both occur at the same time. With all honesty, the first formula that we mentioned about mutually exclusive did not really need to be mentioned. Because technically, if they were mutually exclusive, this just becomes 0 right here. And you're left with the formula that we had in the case it was mutually exclusive. So this is the formula for describing, the possibility of two events occurring, one or the other, or both. So now, for example 4, we can make use of this to some extent because we can say, okay, well, let E and F be two events that are mutually exclusive. I don't know why it says they're mutually exclusive because I can tell you right now they're not. I might have just forgotten to do a cut or paste or things like that. Let's scratch out part of this. They're not mutually exclusive. And they're not mutually exclusive because they do have an intersection. If they were mutually exclusive, then they wouldn't have this value here would be 0. So we're going to let P of E equal 0.38, P of F equal 0.5, and the probability of E and F be 0.15. Compute the following. Well, there's a well-duh question here, a no-brainer. B, because we told you outright what the probability of E is. It's still 0.38. I do have the occasional student, if I don't really ask questions like this very frequently, but I've seen students in the past where I've done that. I say, well, the probability is 0.38. What's the probability of this? It's the same thing. Remember, I gave other information in between, mind you, and I would have students, they'll tell me it's something totally different. It's like, well, no, I told you it was 0.38. That was pretty much, you had to do nothing to calculate that because I told you what it was. So make sure that as you go through things, that you make sure that things agree. Because I've seen students, they'll know, or they'll make a statement, well, the probability of F is this. And then later in the problem, they say, well, the probability of F is this, to make some other calculation work that shouldn't have worked the way it did. So, that's usually a sign, well, if you're telling me it's two different things and it really can't be, then that's a sign that you're making an error at least somewhere. So you need to try to find where that is. As far as the probability of E or F goes, I could just use the formula that we have over here. I know, because I know the probability of E, the probability of F, and the probability of E and F. They're these. And so that's the substitution. And so when I then put them together, the probability of me being in E or F under these conditions is going to be 0.73. The probability of not F, well, there's another rule that basically says a complement. Since we know all probabilities for an event have to total 1, then if I'm doing the probability of, of a complement of an event, then I could say, well, it's just going to be 1 minus the probability of the event occurring. So here I would do 1 minus the probability of F, which is 1 minus 0.5, which is 0.5. So in the case of D, when you start getting complements intersected with non-complements and, and maybe even multiple unions and intersections, here's where it's a good idea to start going back to using the Venn diagram. So I'm going to use a Venn diagram for this last part. I could probably figure out things, but then even to do that, I have to use a formula. We haven't talked about how to calculate the probability of an AND event by itself yet. And even with that, there's two ways of doing it depending on whether or not the events are dependent or independent, and we will get into more into that later, because that's gonna hold a basis as how I calculate that. So I could do this another way that we're going to learn later, but for the time being, we'll overcome that hurdle just by using this Venn diagram, because I have information I could put in here already. Now I'm putting the probabilities in here. I know the probability for E and F is 0.15. I know that the probability of F is 0.5, so that and the 0.15 it shares with E should total 0.5, which means that the probability of being only an F is 0.35. And I could do something very similar with E. I know that I have 0.15 that's being shared with F, and since there's 0.38 total, then the part that's just in E and nothing else would be 0.23. I also know that the universal outside of the two circles is 0.27, because remember, all four of these, all my probabilities together should total 1. So now I'm looking for the probability of something occurring in not in E, but is in F. So I'm looking for the parts that are in F but not in E. So basically I'm looking at this region right here. And based off of that, that's probability is going to be 0.35. Let's go on to the next one here. A leading manufacturer of kitchen appliances advertised its products in 2 magazines, Good Housekeeping and the Ladies' Home Journal. A survey of 500 customers revealed that 140 learned of its products from Good Housekeeping, 130 learned of its products from the Ladies' Home Journal, and 80 learned of its products from both magazines. What is the probability that a person selected at random from this group saw the manufacturer's advertisement in A, both magazines, B, at least one of the 2 magazines, or C, exactly 1 magazine? So take a few moments to answer these questions, and we'll go over it momentarily. Okay. Now, some of this comes directly from the data they gave us. In other parts, I may have to do some diagrams or use some formulas or things of that nature. But the information I'm given here, I'm going to let G be those who got learned of the products through Good Housekeeping, and that probability is 140 over 500, which is 0.28. The probability of them getting learning of the product through Ladies' Home Journal was 130 out of 500, which is 0.26. And both magazines, based on what they told us, was 80 out of 500, and that's 0.16. So these are pretty self-explanatory from the information that they have. Sometimes when you're going to start seeing the term at least one, or at least this, or at least that. And sometimes you might have to interpret what that means in order to know what probabilities you're going to need to find and eventually calculate to get the answer that you're looking for. The probability of at least one of the 2 magazines. Now, there's only 2 magazines mentioned, so basically either they learned the product through Good Housekeeping, Ladies' Home Journal, both, neither, one or the other, that sort of thing. So there's no other magazines mentioned. So when I do the problem, so basically at least one of the 2 magazines means that I'm looking for the probability that of having either a member of group G or a member of group L. And I'm going to use the formula, the addition formula for the probability of union, and that's going to be the probability of G plus the probability of L minus the probability of both. So as you can see there, I worked it out and got 0.38. The last one is asking the probability of getting it from exactly 1 magazine. So one or the other, but not both. That's what this one is. That one's a little harder to do. So in this one here, I am going to employ the use of a Venn diagram. So I set my Venn diagram. I have a circle for G, a circle for L. I've worked out these probabilities already. And very importantly, I also worked out, although it's not needed for this, the probability of, someone learning of their product not in either of these two magazines, because that might play a role too in some questions. So it's always good to make sure you figure out any and all regions that are in your Venn diagram. But I want to figure out the probability of someone learning of this product through only one magazine. So exactly one, so one or the other, but not both. So I'm looking for basically the probability described by these two regions. And so when I make use of that, that means that the probability of getting exactly one magazine, or that someone learned the product through exactly one magazine, is 0.12 plus 0.10, which equals 0.22. Or about 22% of the respondents learned the product through one magazine or the other, but not both. So for example 6 now, in a survey of 2,140 teachers in a certain metropolitan area, there was basically a survey conducted, and they were asked their opinions about attitudes about teachers. 900 of them said they have a lack of parental support and that that's a problem. 890 said that abused or neglected children are problems in their school. 680 of them said that malnutrition or students' poor health are problems in their school. 120 said that lack of parental support and abused or neglected children are problems. 110 said that the lack of parental support and malnutrition or poor health are problems. And 140 said that abused or neglected children and malnutrition or poor health are problems. And 40 said the lack of parental support, abuse or neglected, and malnutrition or poor health are problems in their school. So all three categories. What is the probability that a teacher selected at random from this group said that lack of parental support is the only problem hampering a student's schooling? So take a few moments, figure out how you would figure out the probability for this, and then we'll go over it. Okay. So this one has three different groupings, three different, attitudes or, problems that teachers are listing as issues at their school. So, it's not going to be as easily as some of the formulas that we've been employing up to this point because of the fact that most of those just involve, two subsets. There's three subsets here. So I'm going to have to make even more use of my Venn diagram and kind of do some things I did back in the previous chapter. So when I set this up, I'm going to have a Venn diagram set up here. I'm going to let L stand for lack of parental support. N is going to stand for neglected children or abused children. So that's the group, neglected and abused. And P is going to be for malnutrition and poor health being issues. And I start my way with the most restrictive out. I know there's 40 people that said that all three of these were problems. So that middle region right there is going to be 40. These, I'm getting these from carrying out the fact that there's 40 in all three parts of each group. So when I say there's 120 that think that the two problems are lack of parental support and abused and neglected children, that's including the 40 that's in all three. So I got to exclude those and carry out these calculations as such. So that's how I get the numbers I have in those intersections of where there's only two regions, between them. And then, of course, the rest of them, I'm going to take the 900, the 890, and 680 and subtract away these numbers that have already come up in the previous thing. So that means I would have 710 out here, 670 in the region where N is, and 470 in the region of P that was left over. Although it's not very important for this particular problem, I I could state that the universal outside of this would be 0. So that means that, every teacher that responded at least had one of these as a problem in their school. Um, so there weren't any that didn't say that these weren't problems, and none of these were problems at their school. So, basically the universal, or my entire subset, or my entire sample space is defined by being the region that's encompassed by these 3 circles. But I said that's not as relevant for what we need to do here, because what we're trying to figure out now is what the probability of me picking a teacher from this group that says that the lack of parental involvement or parental support is the only issue. So I'm looking for this, region right here, because those are the teachers that said that that is an issue, but didn't name the other ones as being issues, and that was the only one that they felt was a problem in their school. So as far as figuring out the probability goes, I would do 710 over 2140, and that's approximately equal to 0.3318. So we've already used some counting techniques, but now we're going to go into using some more counting techniques as we go through these last parts of these problems in 7.4. They have this rule placed oddly in the textbook. Don't know why they have it here in particular, because of the fact that, we've already been calculating probabilities using this idea, but basically if S is the uniform sample space and E is an event, then to figure out the probability, I'm just going to take the number of possible events and divided by the number of all possible outcomes. So as an example, here they give us 4 balls are selected at random without replacement from an urn containing 3 white balls and 5 blue balls. Find the probability of the events below. So we're looking for the probability that 2 of the balls are white and 2 are blue. All the balls are blue. Exactly 3 of the balls are blue. And lastly, that 2 or 3 of the balls are white. So take a moment or two, answer the question, and then we will go over it. I'll give a visual here, even though a visual doesn't typically, for this particular problem, is not as useful as it is in some other ones, but nonetheless, sometimes having a visual can help you organize the information a little bit better. So might as well have one. So you're told that you have 4 balls are selected at random without replacement from an urn containing 3 white balls and 5 blue balls. So I know 4 balls are being selected. I know there's 3 white and 5 blue, so there's 8 balls in total. So basically my sample space number is going to be the combination of me selecting 4 individuals from 8. And that's going to give me 56. So, and the order doesn't matter. I mean, it doesn't matter which order I choose whichever ball. So, but I do know I'm picking 4 out of the 8. For part A, you're trying to figure out, what's the probability that 2 of the balls are white and 2 are blue. Well, for me to figure that out, I'm looking for the number of circumstances where I'm going to have, be able to select 2 white balls from the 3 that are in there, and 2 blue balls from the 5 that are in there. So, and the number of possible outcomes is going to be the product of those 2 combinations. So based off of this, there are 30 different ways from these 8 balls that we have, and me selecting 4 of them, that I'm going to have the ability to get 30 possible outcomes where I have 2 white and 2 blue, and that's 30 out of 56, which gives me about 0.5357. That's the probability. The probability that all the balls are blue. So looking for the probability that all are blue. That's me having, out of the 5 that are blue, I'm picking 4 of them. So that's how many different ways I could possibly have that occur. So the probability of me getting all blue would be 5 out of 56, or 0.0893. The probability of exactly 3 of the balls being blue. So that means that I'm going to have 3 blue and 1 white. So the number that happens with that is basically the combination with n being 5 and r being 3 as well, times the combination of n being 3 and r being 1. And then ends up being 30. And so it's 30 out of 56, which is going to give me the 0.5357 again. So this has the same probability as having 2 balls for being white and 2 being blue. For D, even more, it's more inclusive. Usually the more inclusive they get, the more difficult it can sometimes be in calculating them. I'm looking for first I'm going to look for the number that has 2 white or 3 white. So that's going to be me taking the numbers where I have 2 white and 2 blue and adding it to the numbers of outcomes that have 3 white and 1 blue. To come up with the number that for 2 white and 2 blue, I'm going to do the combination for n being 3 and r being 2 times the combination of n being 5 and r being 2. To come up with the number of outcomes that would have 3 white and 1 blue, I'd be doing the combination of, where n is 3 and r is 3, as well as one that's going to have the combination of n being 5 and r being 1. So basically, there's 35 different outcomes that are going to have either 2 white balls or 3 white balls, or both. And that's going to be, as a probability, 35 out of 56, which is 5/8, which is 0.625. Example 2. 2 light bulbs are selected at random from a lot of 24, of which 4 are defective. What is the probability that A, both of the light bulbs are defective, and B, at least one of the light bulbs is defective? So take a moment or two, answer these questions, and then we'll go over it. Okay. Kind of an unrealistic circumstance, because usually if you're doing quality control, you really don't know how many are defective out of a lot, They do product testing, and they, look for certain standards, and, there's more complicated statistics let them come up with like a number to say, okay, if this many are defective, we're going to throw the lot out. But here we do, or at least we're given that we have a lot size of 24, 4 are defective, which means we have 24 light bulbs. 4 of them are defective, which means 20 of them are working. So with that information, these calculations are a little bit easier to do because they're, and we're going to talk about independent and dependent. These events are dependent on each other to a certain degree, because once I choose one light bulb, that's going to affect the probabilities, of me picking another light bulb with a certain characteristic, because one's now missing. Whereas, in the next one we're going to do towards the end of this, we're going to have circumstances where they are independent, which means one does not, have any influence on the other. But we'll get back to that in a second. We know we're picking 2 light bulbs. I also see this at least 1 at the bottom there, which means, that could sometimes be a little bit on the complicated side. Because that means 1 or more. And, there's different ways of me handling it. So for me to answer both these questions, it might be a good idea for me to set up a probability distribution table, where I'm going to let X be the number of defective bulbs. And really, because of the way it's described here, 0, 1, and 2 are my only possible outcomes. I can either have 0 defective light bulbs, 1 defective light bulb, or 2 defective light bulbs, because I'm only picking 2. I'm going to work out these probabilities. The probability that none are defective means I have basically the number of outcomes where all of them are working, or both of them are working, over the sample space number. The sample space number is me picking 2 bulbs from a group of 24. So the combination where n is 24 and r is 2 is going to be the denominator for all of these. If I have 2 of them that are working, then I'm looking for a combination where I'm picking 2 from the 20 that are working. And that's going to give me my numerator number, and this probability ends up being 0.6884. If I have 1 working and 1 defect, then basically I'm going to have the combination of n being 20 and r being 1 to represent the working light bulbs numbers, or number of outcomes, and I'm going to have C of 4, 1 represent the number of outcomes for choosing 1 from the defective group. If I multiply those together and divide by the C, where n is 24 and r is 2, I get 0.2899. And for 2, I'm still calculating it a very similar way, but I'm going to be able to do something to check to make sure that I'm more than likely right in a moment. So I'm going to look for a number of outcomes where there's 2 defects over the total number of all possible outcomes. Again, the number of all possible outcomes is C, where is a combination where n is 24 and r is 2. To have 2 defects, it means I'm picking 2 from the group of 4, and I'm looking for the number of combinations for that. And when I divide them, I get 0.0217. One of the things I could do to check that these calculations were right is make sure they do total 1, and they do. So these seem to be on the right track. So when I look at the first one here, what's the probability of both light bulbs being defective? Well, that's the probability that x equals 2, so that was worked out when I made the table itself. The probability of at least 1, well, I could add up the probabilities of 1 and 2, add them together, and get 0.3116. One of the things we're going to make use of, and you're going to see me use it momentarily, is that I could have also calculated by saying, well, the probability of being 1 or more is 1 minus the probability of having none. And if you have a situation where the probability distribution you would have would be quite long, and the prospect of adding the probability where x equals 1, 2, 3, 4 for some huge number is not really going to make things a little as simple for you as possible. It's going to certainly overcomplicate things. So some ways, an easier way to calculate is say, well, the exact opposite is the probability that I have none that are defective. So in this case here, I'm just going to do 1 minus that, and that should give me the probability that I have 1 or more that are defective. So as you can see there, when I do that, I do 1 minus 0.6884, and I get the 0.3116 that I got in red. So either way, it calculates it correctly. Now, this question here, very similar because of the fact that, we're being told that we have 20 words in total. 12 of them are known, 8 are unknown. And so you're being asked that, if there's 10 words on the test, what's the probability that at least 8 of those words are ones that the student already knows? So take a moment, figure out how you would answer that question, and then we will go over it. Okay, so with this information here, I know there's 10 words on the test. So I know that my sample space number and I said probability here, it should really be number, not P of S, but N of S. So let me take care of that really quick. This should be N of S. Is the combination where N is 20, R is 10. So there's basically 184,756 different outcomes. I can pick 10 vocabulary words from the 20 in total to make up the test. What I want to do is figure out the probability that at least 8 of the words on the test are words that the student already knows. So I'm going to let x represent the number of known words. I know the probability of x being greater than or equal to 8 is going to be the probability of x being 8, the probability of x being 9, plus the probability of x being 10. So that was pretty straightforward to go that way. Say I just need to find the probabilities of 8, 9, and 10, and then add them together. That's going to give me the probability I'm looking for here. So I calculate these probabilities. So the top, so for me to get 8 of the words that I know on the test, for me to get 8 words on the test that that the student already knows, I'm going to do the combination of N being 12 and R being 8 to represent choosing 8 words from the list of those that he knows, and times the combination of N being 8 and R being 2 to represent the number of possible outcomes where I'm choosing 2 out of the 8 that he does not know. Then I do the same thing for 9, except now I'm going to have the combination where N is 12 and R is 9 times the combination where N is 8 and R is 1. And the last one, the combination of 12, 10, that's basically a circumstance where I'm taking, because I'm saying that all 10 are from the group of 12 that I know, or the student knows, so I'm going to choose 10 out of that 12 and divide that by my NS, and that's going to give me these numbers here. And so when I add those probabilities together, I get 0.08490. So the possibility or the probability that at least 8 of the words, 8 or more of the words that are on this test are going to be ones that the student already knows is about 8.4%. So not really a huge percentage, so it would be a good idea to learn the other words. So this last circumstance is quite different. In the previous ones, we had a defined group of a certain number that had certain characteristics, and that we were picking basically subsets of a smaller number from it. I don't have that here because I don't know how many of each, how many are in each one of these groups. I do know that 5 people are being picked, and we're looking for the probability of at least 2 of them having the characteristics that are named here. In A, the characteristic is that they have the same sign. Doesn't say which sign that is, but they have the same sign. And B, they're born under the sign of Aries. So take a moment or two, try to see if you can answer this question and come up with the probabilities for these, and then we will go over them. Okay, for the first, for both of these, we have to be aware that there are 12 signs of the zodiac, which we're told in the problem quite, specifically. When I look at the probability of at least 2 of them having the same sign, well, for me to say that any of them have the same sign, I have to have 2 or more people have the same sign. So if I think about it, the exact opposite of at least 2 of them having the same sign would be the exact opposite of none of them having the same sign, or all the people's signs being different. So I can think about the probability of at least 2 with the same sign being equal to 1 minus the probability that all of them have different signs. Now, I'm not going to be able to use combinations here because I don't have group sizes that are of specific amounts. I don't have like I don't say I'm picking 5 people from a group of this many Geminis, this many Virgos, blah 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 blah. So I can't use combinations for these. I'm going to have to use basic logic on this and basically fraction knowledge. Because for me to get the probability that all have different signs, okay, I'm going to basically be taking 12 out of 12 times 11 out of 12 times 10 out of 12 times 9 out of 12 times 8 out of 12. I mean, the first one being 12 out of 12, I mean, I don't know, they're not saying which sign is it under. So, I mean, I could have 2 that are Aries, 2 that are Tauruses, 2 that are Sagittariuses. It doesn't matter. As long as there's 2 or more of any one group or any sign, that's what we're looking for. So when I look at this, I mean, the probability of me having a person that has one of these signs, well, it's 12 out of 12. I mean, they have to. Now, for them to say it's different, the next person, the probability of that next person being chosen has a different sign is 11 out of 12. Because, there's still 12 zodiac signs. They're not exhausted. But now there's only 11 from which to choose from for that next person. So there's 11 out of 12 chance that that next person is going to have the same sign or have a sign different from the person before them. And then 10 out of 12 because the next person, there's now 2 of the signs have been picked, and it's all the way down the line. And if I do 1 minus that, I get about 0.6181. So it's a pretty decent sized chance that, I mean, even though I'm just choosing 5 people at random, I have about a 61.81% chance that I can get at least 2 of them to have the same zodiac sign. For part B, I'm going to let X be the number of people who are under the sign Aries. And I'm also going to make the contention here that under those kind of conditions, the probability of X being greater than or equal to 2 equals 1 minus the probability that X is less than or equal to 1, which means I'm looking for the 1 minus the probability of 0 plus the probability of 1. The reason why I'm doing that is, I mean, technically I'm looking for at least 2 of them being born under the sign of Aries. That means I have to do the probability of 2, the probability of 3, the probability of 4, the probability of 5. That'd be 4 probabilities I have to figure out if I did it that way. Whereas this one here, I really only need to figure out 2 probabilities. The probability of none of them being born under the sign of Aries, or just one of them being born under the sign of Aries. So those are, I mean, that's 2 calculations compared to 4, so it's a little easier. Well, there's 11 zodiac signs that are not Aries. So the probability that I have someone who is not an Aries is going to be 11 out of 12. And so I would do 11 out of 12 times 11 out of 12 times 11 out of 12, so 5 times, and get 0.6472. They ask questions like this even in this section, even though it's kind of getting into the next set of rules for probability, me multiplying them together, and these are independent events. I mean, one person's zodiac sign is not going to necessarily have an effect on another person's zodiac sign, especially if they're not related in any way. Obviously, if you're looking at twins, that's a different story. But, if you're just looking at random people being chosen, then my zodiac sign is not going to have an effect on that person's zodiac sign. I mean, we're already born. I mean, so, that's my zodiac sign is not going to have an effect on what someone else's zodiac sign is going to be. So, the probability of having one person that's an Aries and 4 that are not is going to be, well, a lot of people think it's this. I mean, just this by itself. Well, obviously, that would be one person. It would be 1 out of 12. It would be a 1 out of 12 chance that person has the zodiac sign Aries. The next 4 people are each going to have 11 out of 12 chance of being one that doesn't have Aries. The problem is, if I look at it from that perspective, when I'm mapping it out this way, that's also considering the order in which they're being chosen. So for this one here, I mean, yes, if I was saying that, that this probability, if I just looked at that, is just the probability that the first person chosen is an Aries and the next four are not. That's not the I mean, that's not the only circumstance where I could possibly have, one person being an Aries and four people are not. It could be that the last person chosen is an Aries and the four that preceded him were not. It could be that the first two are Aries, or the first two are not Aries, the third one is, and the next two are not. So I have to think about, well, how many different possibilities, how many possible ways could I get one person that is an Aries and four people that are not? And there's 5 different ways for that to happen. So, and that's basically kind of getting into some of the combination stuff and things like that. So sometimes you get permutations and combinations working simultaneously. So here, I'm going to have 5 times this product. That's going to be the number, that's going to be the probability of people having, one person being an Aries and the other 11, or the other 4 not. So that's 0.2942. So if I want to calculate the probability that someone was born under the sign of Aries, I'm going to do 1 minus the sum of those two, which gives me 0.0586. So basically, if I have 5 people being chosen, the probability that at least 2 are under the sign of Aries is 0.0586, or about 5.86%. The reason why I make sure to show this is, one, it kind of gives you a look ahead. Even though they have problems like this in this section, it's more apropos for what's coming up in the next chapter, or next part of the chapter. So it's a good look ahead to what we're going to be doing more of in the next couple of lessons. And secondly, a lot of people will look at these as being the exact same thing. At least 2 people with the same sign, or at least 2 that are Aries, will say, well, they're the same thing. And they're really not. I mean, because the first one isn't really defining what sign it is. So it's far more inclusive than me saying, well, at least 2 are Aries, because I'm saying it's only that one I'm looking at. So, if you want to think about it, the probability of at least 2 Aries is 0.0586. Well, this is what I would expect to be the probability of getting at least 2 Cancers, at least 2 Capricorns. And so basically, if I'm looking for the probability that at least 2 are with the same sign, it should be basically me being able to take 0.0586 and multiply it by 12, because there's 12 different outcomes, and I should get something kind of close to what the other one has. Now, it's not quite the same, but it's a good approximation, because, I mean, some of it's due to rounding things that we did along the way and things of that nature, so you have to keep that in mind. But there's your probabilities for these 2 circumstances. If you have any further questions, make sure to bring them up in class, and I'll see you there. Have a good day.